Unit 2, the atom, chapter 1. This unit begins kind of a little bit more of a specific talking about chemistry, whereas the last couple units were talking about not really chemistry as we might think of it, but chemistry in a different way. Whereas this we actually talk about the atom. Now the topics of discussion that we had in Unit 1 and Unit 1.5 are going to be important as we move forward, as everything we do in this class is something that's cumulative, so you can't just all of a sudden forget what you have been looked at and taught before. And so this unit is kind of really starting to become the building for units to come. First off, some background knowledge. The atom is the smallest particle that an element that retains its identity in a chemical reaction. We looked at these as a pure substance. An element is a pure substance. Well, the element is made of, or elements have atoms that are all similar in some way, and they keep their identity in a chemical reaction. Now, what the atom looks like, or what how the atom interacts with some things, and at the very early points was very debated, very highly debated, and philosophers and scientists have had a lot of different ideas. In Unit 1, we talked about the models and how do we know if a model is true. Well, some of the models that we have currently are based on math, being that it shows us some math and some experimental data that shows that atoms exist and that they have certain behaviors. Exactly how do they look? Not really quite sure. We've never been able to take a photo of them per se that shows them with their Mickey Mouse hat on visiting Walt Disney World. So there's just a lot of different ways to kind of think about as we go through this. Kind of the earliest topics of this was brought up by a man in 400 BC, Democritus. And now BC counts backwards, so it will go 400, 300, 200, and stated that matter is consisted of tiny indivisible particles. I mean, you can't see them. They are invisible and indivisible, meaning they cannot be divided. And he called these things atomos, which we kind of use as a kind of a homage or kind of using of that Greek word. And Democritus says that these particles are invisible. We can't see them, and they can't be divided. Well, in some ways he's correct, and in some ways he's not correct, if we really look at it. Well, about one of his students, Aristotle, and I believe Plato was another one, that did not, or Socrates, Aristotle, and Plato did not fully agree with this idea of Democritus, and instead said that matter could be divided in an infinite number of times. This idea was, and from a very conceptual point of view, makes a lot of sense. In that, if you take a grain of sand or a rock, let's just get something nice and big, like a big rock boulder that requires two hands to hold up, and you drop it on the ground, and it breaks, and it's broken, and you take that smaller chunk off of it and break it some more, it's still part of that rock that you originally had. And if you take that rock and you keep breaking it and breaking it and breaking it, and so much so that you're down to the kind of the size of a grain of sand, and now you're like, okay, it's still part of that rock. No matter how small this is a grain of sand. It's just something from something bigger. It's just something small from something bigger. So if I crush it even more with like a rock hammer and start pulverizing it, and it becomes this very fine dust. Well, even just those grains of fine dust came from something. And this was the idea that Aristotle proposed, is that these atoms are nothing more they can't exist, because if I take that rock and I break it apart, no matter how much I break it, those small particles are still a part of that bigger rock. And it makes sense. Heck, it makes sense to me in some way to think about it that way. But the question they weren't asking themselves was, what makes up that rock? What are the parts that make up that rock? And so that's the question that they failed to ask. Their idea or their concept that matter can be divided in an infinite amount of times held for over 2,000 years. And so we can see why progress in some ways was slow up until a certain point. Now, my suggestion is make note of dates of when and who and what did they do. And so that will make your life a little bit easier when you're kind of putting this all together, and so you can kind of see it written out in kind of like a timeline fashion. And so we look at these first things that I have underlined in here. So the very first thing would be 400 BC, Democritus, atomos. What did he do? The dates, I'm not going to worry about the dates on a test or a quiz. The dates are just so that you kind of see the chronological order in which these go. The ancient Greek philosopher, credited with suggesting all matter is made of indivisible atoms, is. Now, a number of years later, in about the year 1808, John Dalton came up with his atomic theory, and it was based on a lot of experimental evidence. Now, John Dalton was a British school teacher. Sometimes he's considered to be what's called an English school teacher, but he taught school in Britain, and a lot of his ideas were based on some other people's stuff. And it's not that he didn't. What he did is he took other people's data, put it together, and proposed new ideas based on these data that some people haven't put together, and say, hey, look, these things connect. And so that allows Dalton's theory to kind of be put together. First point that Dalton came up with is that all elements are composed of tiny indivisible particles called atoms. And here's some arbitrary model of some atoms of element A. And so we have atoms of element A, whatever it is, doesn't matter. And so it brings us back to that idea of Democritus, that these all elements, because they were able to actually start figuring out. And it wasn't that scientists didn't think that there were still just 4 elements, but they knew there was something else. And so to try and really break those barriers, that understanding that matter can be divided in an infinite amount of times, they needed some more than that. They needed experimental evidence, and that's something that we have to work at. And so there was experimental evidence that said that elements are composed of these things called atoms. And how that goes, we'll eventually look at as well. So it's just the beginning parts of that. And so the first point, very important. Okay, but again, we can't see them, but they're there. Atoms of the same element are identical. Should make sense. Gold atoms are identical to gold atoms. Oxygen atoms are identical to oxygen atoms. Silver atoms are identical to silver atoms. And atoms of one element are different than elements of another. As we can see, element A, they all look the same. Element B, they also look the same. But element A and B, they are not the same. So these guys, hey, look, that's the same, and 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 these guys are the same, and that guy's the same, and that guy's the same to that one, and that one to that one, so on and so forth. But here, they're not the same when it comes to comparing themselves with others. So they are not the same. They can physically mix together. So you can physically mix some of these atoms together. And they can combine, making compounds. And they do so in simple whole number ratios. That is an important part, is these whole number ratios. So we don't get like partial amounts of a oxygen atom, or partial, like a half of a hydrogen atom. Trust me, if you have a half of a hydrogen atom, we have some major issues. And so you have these whole number ratios. It actually makes our life a whole lot easier dealing with whole numbers versus partials and or fractions. Now, the next two here are chemical reactions occur when atoms are separated, joined, or rearranged. As we saw, ways in which we can identify whether or not a chemical reaction happens are through this, that these chemical reactions occur when something is joined, rearranged, or separated. As we look at it even more specifically as we move forward, when we look at types of chemical reactions. Atoms of one element are never changed into atoms of another element in a chemical, and that should say reaction, as looks like the reaction there, as the image kind of broke that up. But in a chemical reaction, and what means you're not going to get turning lead into gold. Sorry, any of those alchemists that thought that was still going to happen. It's not. And so a chemical reaction is not going to make something else. They can combine, as we can see these little A's and B's making what looks to be water atoms. Or molecules, I'm sorry. And so we have this thing can happen. They're not rearranged, they're not split apart. If they do, the atom does break apart, there's a lot of energy being given off. And that's why we say in a chemical reaction, because if an atom does split, you have a nuclear reaction, and well, like I said, things change. Dalton's atomic theory improved earlier atomic theory by individual atoms are observable with It was later discovered that not everything was correct, although it was an excellent start, but not everything that Dalton said was spot on, meaning you got some work to do yet, John Dalton, sorry. But that's actually awesome, because that tells us that science is ever changing, and that just because we think one thing doesn't mean that it's going to be the way it is for all time. And so we look at that as that people explored and said, well, I don't believe that the atom is invisible or indivisible. I think there's something more to it. There's some evidence here, and people became inquisitive. In a way, you can look at it as that scientists they're not like social deviants, but they're deviants amongst the science society. People look at the absolute zero, for example. Last unit we talked about 0 Kelvin being absolute zero. Nothing gets colder than absolute zero. And people look at say, well, why? Why you say we can't reach absolute zero? And so people actually start pushing those boundaries. That's how advances in science happen, is when someone says you can't and someone goes, well, I'm going to. And so they work at it. Faraday and Crookes were among the first to discover some of these things and some of these subatomic particles, especially the electron. Now, J.J. Thomson was who characterized the electron a little bit more thoroughly, and gets therefore a little bit more of the credit to deal with. And when we talk about subatomic particles, we talk about them a little bit differently. And the first thing we do is actually talk about the electron. But before we talk about the electron, we should probably talk about the other one of the other subatomic particles, and actually the one that gets a little bit forgotten about. And that's in 1886, Eugene Goldstein observed a cathode ray tube and found that rays traveled in the opposite to the cathode. You have an anode and a cathode, and they were moving the opposite way. And so he figured that these subatomic particles must be protons. Now, again, remember, they knew that the electron was there based on Faraday and Crookes, but they didn't quite know that much about the electron. They knew these you would get these cathode rays and kind of go from there. Well, no, the proton is a very important subatomic particle because it defines what the element is. The number of protons defines what that element is. And we use a kind of a shorthand notation of a P, and in some cases you'll see it a plus. It can be superscripted or not superscripted as it's here. A subatomic particle having a mass of almost 2,000 times greater than that of an electron. So you look at this and we see that Eugene Goldstein in 1886 observed proton in subatomic particles, protons, cathode ray. Is kind of really what you're looking at. And he's one that a lot of books don't like to mention as having found the proton. And reason for that, I think, is that the electron's finding is a little bit more brought upon, is because in 1897, that's not very long afterwards, you have J.J. Thomson here not just discovering the electron, characterized it a little bit more. And we start looking at the electron as a small, and when we say it's small, it is small. 9.11 or 9.107 times 10 to the negative 28th grams. A lot of times you'll see it actually written in kilograms, and so therefore it's going to be even smaller of a number. That scientific notation is definitely understand that that's a very, 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 very small number, and so we have to understand that the electron is extremely small. Now, 2,000 times more massive than that might not seem a whole lot, but when you're dealing with the scale that the subatomic particles are, the electron and the proton are at, 2,000 times is an extremely more significant, and it's just a massive amount of that. Thomson performed some experiments that involved passing the electron current through gases at low pressure. Now, this result showed that, and what Thomson did also is he took this little magnet here, and I'm going to just draw a little horseshoe magnet. It's not going to be probably the best one ever, but you know, I was never an art major, but I'm going to give it my all here. And so we have this little horseshoe magnet. Put one end on the side there, and we'll just go under the impression that it's somewhat the same. And what that did is that some of those particles kind of curved up towards the magnet, and some of them just kind of went away from the magnet, as we can kind of see, a little bit of away from the magnet, or it went straight ahead. And so what he was like, hey, this means that there must be a magnetism, meaning there must be a charge, and so we look at that as the electrons. I think there's a better visual in your book that I used to kind of better describe this, but that's essentially kind of what happened. He's like, hey, look, played around with some light and put a magnet there. If you have a CRT monitor or a tube-based TV, you can still kind of see this by putting a magnet. I wouldn't suggest holding it there for very long, but the colors distort because you are pulling the photons, the light, towards it, and it's going to change how the color looks. About 12 years later, Robert Millikan ran the Oil-drop experiment. Now, what did this oil-drop experiment look like? It's one of those interactive illustrations that I have linked in your book that I would suggest looking at, and so you can actually see and actually play with Millikan's Oil-drop Experiment. This is something that a lot of high school curriculums don't look at. I think that it's something that a lot of college curriculums do look at because of what is done with this. Because using Thomson and Millikan's results, you can actually calculate the mass of an electron, because you're not going to take and pluck an electron out of an atom and set it on a scale and go, oh look, it weighs 9.1 times 10 to the negative 28th grams. It's not going to happen. You have to figure out some other random way, an indirect method at finding something so difficult. And so we used Millikan's experiments to do that, and he was applying voltage between two plates. And if he can adjust the voltage very finely, you can get some very, very accurate results. Taking into account the gravity, the mass, and some of those types of things, you can find some more information out about these. And it's extremely, I think, valuable information that we don't actually maybe look at all the time. So it is there, and so we look at it. And so we can see that using those two results, it can give us some very valuable information. Again, I would look at the interactive image that's in your book and click on the link and play around with the voltage that the best that you can, and you can kind of see how that looks like. And I think it's important to note that Millikan built this oil drop experiment because he had to figure out, okay, how do I build something that can do this thing? And so I think it leads us to a little bit of an appreciation for what these men and women did to do what they did. And so I think we have to be kind of mindful of how that works. And the last subatomic particle that we haven't talked about yet is the one that in 1932 we have James Chadwick discovering the last one. Confirm the existence, as I really like that way in which we say it. Confirm the existence of the neutron. And the neutron, we say confirm the existence because things weren't matching up. The mass of the electron and the proton didn't add up to the mass of the atom or some atoms, and things weren't adding up. So they suggested that maybe there's something else, this other subatomic particle that maybe doesn't have a charge. The other subatomic particles were found using electricity. Because they were using electricity, they're easy to find. There's a positive and a negative, and you can find those parts of it easier. Well, when something doesn't have a charge, it makes finding it a little bit difficult. And so James Chadwick kind of went around a little bit similar method as the cathode ray tube, but he was using, I believe, some radioactive material and was able to catch it in a wax and figured out how much the wax weighed before, after the experiment, and then looked at what happened. So James Chadwick confirmed the existence. It was thought about, it was widely accepted in the scientific community, but it needed that confirmation, needed that experimental evidence that, hey, look, this does exist. Which of the following is not an example of a subatomic particle? The nucleus of an atom consists of